Hi all. Today let us discuss on the topic quarks. Quarks are actually the ultimate constituents of hadrons. The scientist George Wing in 1963 proposed that all baryons consist of three still more fundamental particles, and the scientist Gell-Mann called these particles as quarks. The name quarks came from the phrase three quarks for mustard mark that appears in James Joyce's novel The Finnegan's Wake. The quarks are further classified into three and are called as up, down, and strange. And these are respectively represented by the symbols U, D, and S. Whereas the U and D quarks have the strangeness number S equal to 0. The S quark has S equal to -1. This is because each baryon, that is the B equal to 1, is made up of 3 quarks. The baryon number of a quark must be B equal to 1 by 3. And in the case of antibaryons, B equal to and the case of antibaryons, the B equal to -1 and are made up of 3 antiquarks. So, the baryon number of an antiquark must be B equal to -3. Mesons, for which the baryon number B equal to 0, consist of a quark and an antiquark. Thus, the quarks all have spin of 1 by 2, which accounts for the observed half integral spins of baryons and 0 or integral spins of mesons. In order for hadrons to have charges of 0 or integral multiple of plus or minus e, the various quarks must have the fractional changes. No other particles in nature have fractional charges, which make the quark hypothesis hard to accept at first. The most direct experiments that point to the reality of quarks involve the scattering of high energy electrons by protons, which reveal that there are indeed three point-like concentrations of charge inside a proton. Quarks are thought to be elementary in same sense as leptons. Now, this is the figure which shows the quark compositions of spin of 1 by 2 baryons. And it illustrates the quark models of nucleons and antinucleons. Now, let us look at a serious problem, that is, the idea that the baryons are composed of quarks was that the presence of 2 or 3 quarks of the same kind in a particular particle. That is, for example, 2 U quarks in a proton and 3 S quarks in an omega baryon, it violates the exclusion principle. Quarks are ought to be subject to this principle since there are fermions with spins of 1 by 2. To get rid of this problem, it was suggested that the quarks and antiquarks have an additional property of some kind that can be manifested in a total of 6 different ways, rather as electrical charge in a property that can be manifested in 2 different ways that have come to be called positive and negative. In the case of quarks, this property became known as color, and its 3 possibilities were called red, green, and blue. And the anti-quark colors are anti-red, anti-green, and anti-blue. According to the color hypothesis, all 3 quarks in a baryon have different colors, which satisfies the exclusion principle since all are then in different states, even if 2 or 3 are otherwise identical. Such composition offers white by analogy with the way red, green, and blue light combine to make white light. There is no connection except on this metaphorical level between quark colors and actual vision colors. Similarly, an antibaryon consists of an anti-red, anti-green, and anti-blue quark. A meson of a quark of one color and antiquark of the corresponding anticolor, which has the effect of cancelling out the color. The result is that hadrons and antihadrons are colorless. Quark color is thus a property that is significant with the hadrons but is never directly observable in the outside world. On a deeper level, the stronger interaction can be considered as being based on quark color, just as the electromagnetic interaction is based on electric charge. Now let us look at the flavor. Not only do quarks come in three colors, but additional varieties of quarks have to be included in scheme to supplement the original U, D and S trio. The first of the new ones, the charm quark C, that is represented by C, was proposed largely by the analogy with the existence of lepton pairs. If quarks are elementary particles in the same sense as the leptons, then there ought to be pairs of them too. This may not be very much of an argument, but so significant have symmetries of various kinds proved to be in physics that it is actually quite reasonable. Such a quark has a charge of plus 2 by 3e and a charm quantum number of plus 1, and other quarks have 0 charm. Charm apparently influences the likelihood of certain hadron decays, and both charmed baryons and mesons that contain C and C bar quarks have been found. Amazingly, all properties of ordinary matter can be understood on the basis of only two leptons. The electron and its associated neutrino and two quarks up and down constitute this first generation. The second generation of two leptons and two quarks, that is the muon and its neutrino, the charm and the strange quarks, are responsible for most of the unstable particles and resonances created in higher energy collisions, all of which decay into members of the first generation. In the third generation, the leptons and the tau meson, whose mass of 1.7 Ga electron voltage is nearly twice that of proton and its neutrino, and the quarks are thus known as top and bottom, and the both are extremely heavy, many times the proton mass, which is why hadrons that contain them can be produced only in the highest energy levels. And the existence of bottom quark was verified in 1977, and that of the top quark was not verified until 1995. Now let us have a look at what is quark confinement. For all the persuasiveness of the quark model of hadrons and for all the searching that has gone on since 1963, no quark has ever been isolated. The present status of quarks may seem like that of neutrinos for 25 years after they were proposed. The reality is suggested by a wealth of indirect evidence, but something in their basic character impedes their detection. The parallel is not really accurate, however. The elusiveness of the neutrino was due merely to its feeble interaction with matter. On the other hand, a fundamental aspect of the color force seems to prevent quarks from the other hand, a fundamental aspect of the color force existing independently outside hadrons. Indeed, the detection of a free quark would represent a failure of the theory called the quantum chromodynamics, which describes their behavior. The explanation for the quark confinement begins with the idea that, as though they were connected by a spring, the attractive force between two quarks goes up as the quark moves apart from their normal spacing. This means that more and more energy is needed to increase their separation. But with enough energy added, instead of a quark breaking free from the others in a hadron, The excess energy goes into producing a quark-antiquark pair. This results in a meson that does escape. That does escape. Thus, when an energetic gamma ray photon impinges on a neutron and causes a UU bar quark antiquark pair to come into being. Thus, the net reaction can be represented by the equation as shown, where gamma plus the neutron gives the proton plus the pi minus. Thus, the quark confinement is not only the example in physics of all of the things that cannot be separated. The north and south poles of a magnet cannot be free from each other either. If you pull apart a magnet so that it breaks, we then have two magnets, each having a north pole and a south pole instead of the independent north and south poles. And that's the end of the seminar, and thank you.